All right, so this afternoon I thought what it would be a good thing to do would be to show you some uranium. In several of the videos previously you've seen various forms of uranium, and one of them was just the metal, but it always appears black. And it appears black because it's got these oxide surfaces on it. But actually uranium, just like lots of other metals in the periodic table, should be a shiny, silvery appearance metal. So I just thought I'd take this opportunity, we'll go in the lab and we'll clean some up, and I'll show you some actual naked uranium, if you like, because it's really very pretty to look at.
My colleague and co-presenter on these videos, Steve Liddell, has got a big grant to study the chemistry of uranium. Chemical research is really quite expensive. You have to pay for the chemicals, the equipment, and the salaries of the people that do it. And Steve has been very fortunate to get a grant from the European Research Council, which gives grants to young researchers all over Europe. So we're very proud of him. And more excitingly, it's going to lead to lots of new chemistry of uranium.
Right, so what we've got here is a beaker which contains some uranium turnings. And as you can see, they look kind of dark in colour. Normally they look really black under the oil, but as we've got them out and we've thinned them out a bit, you can already start to see shiny edges on them, because actually that's the true colour of uranium. It was originally a block of uranium and it was machined on a lathe, which has just turned it all out as little turnings, because that's much easier for us to handle because it's got a bigger surface area. And uranium as a metal is really very hard, so you can't just saw an edge off it, because you'd actually blunt the saw before you would actually get a bit chopped off. So you have to use really hard drill bits to get this uranium turned off. Now it still looks fairly dark, and that's because it's got this oxide layer on it which has passivated it over time, because uranium's quite a hard metal, so it likes to be bonded to hard elements like oxygen. We're going to get rid of this oil and wash it a few times just to make sure it's free of that, and then we're going to treat it with concentrated nitric acid. And the nitric acid attacks the oxide layer and pulls all the oxygens off and just leaves you with a nice shiny uranium underneath. And when it does that, it gives off clouds of NO2, which is orange, so you start to see that coming off in the solution darkening. And then what you should see after we've washed it a few times is the nice shiny metal surface, and that was actually there all the time underneath.
I think it is about €1 million, so it's really quite a large sum of money. That's $1.5 million, so it's a lot of money, but it's over 5 years, and will pay for a good team for him to do his research with. And so I think we can look forward to a lot more new compounds on YouTube.
Like all our uranium in the lab, this is depleted, which means that essentially all of the radioactive component has been removed. So this is essentially non-radioactive. It's toxic as a heavy metal would be, like lead, but it's no worse than lead, really. I'm just weighing it now, because part of the rules that govern the fact that we're allowed to use this stuff is that we have to keep an accurate measure of how much we've used every time. Okay, so now we've got these turnings, they're free of the oil, and we're going to treat them with concentrated nitric acid, which is going to clean them up. This is a very strong acid, so you have to handle it quite carefully. Chemically right now, the HNO3, which is the nitric acid, that's reacting with what on the surface is UON. We don't know how many oxygens there are. I suppose X would be better than N. And it's going to react to make water and NO2. So that HNO3 is going to fall apart and reorganize. And as you can see now, the solution's starting to get a little bit of color to it, and that's because the cognito is attacking this oxide layer, and it's generating little bits of NO2 which are going off, and it's generating water at the same time. So it's got this sort of yellow colour to it already. So there's not a large amount of NO2 being given off, but there's a little bit. If you get really reactive, very small uranium turnings, sometimes you get like clouds of NO2 coming off. So that the trick with this is to leave it just long enough that you get rid of all the black oxide layer, but not too long that you start eating away at the actual nice shiny metal as well and end up with nothing left. So you just have to keep an eye on it. But all the time you can see the solution's getting darker and darker, and that's because of this NO2 component coming off. Right, and then we're going to tip this out and pat them dry. So there you go, some naked uranium. I mean, to the eye that would look like just any other metal, and to all intents and purposes, because the radioactive component is gone, that's all it is. It's just another metal in the periodic table. Only it's the boogeyman. Well, if I just left that in that weighing boat, slowly but surely the surface layer of the uranium would start to react with oxygen in the air, and it would start to darken again, and you'd get this thick oxide layer building up again. So we have to put it in an ampule and get it away from air, and then it will stay intact. Well, the future of that uranium there is that we will react it with iodine and turn it into uranium triiodide. And that's one of our start materials to make these interesting compounds, because you can exchange the halides for other groups which make it much more soluble, and you can get them in a solution and then crystallize them out and make very nice crystals of compounds.